The atomic mass is the number of protons and neutrons together. You add them together. Atomic mass is protons and neutrons together. Atomic number is only the number of protons. So to find the number of neutrons, you would subtract the number of protons from the atomic mass. So atomic mass minus atomic number gives you the number of neutrons. Now you got to round to the nearest whole. What is a family of elements?
The vertical columns.
It's a vertical column, and they share what? Certain
Mass. Elements.
Per-
Protons. Peroxide.
Properties.
peroxide. Properties, guys. Certain characteristics, right?
Yeah.
So those vertical columns they have similar properties. Those elements, we call them families of elements because they have. My dad and I, if you were to listen to both of us on the phone, you'd be like, "Oh, who am I talking to?" Her and her mother sometimes somebody will answer, like, who am I talking to?
Atomic mass is 19 exactly.
19.
Yeah,
What?
19 minus
No, the atomic mass is 35.45 something or other. But we round down to the nearest whole. Okay? So it'd be 35 is the atomic mass. Because you can't have part of a neutron. Does that make sense? So you just round. Now, if you want to be more specific, we'd have to know exactly which isotope of chlorine we're dealing with. Does that make sense? No? All right, so the atomic mass number on the periodic tables. I want you to look at it. Pull out your here. I'll give you a new one. In fact, I'm going to give you guys the cream of the crop. All right, I'm going to give you all this U.S. Navy provided amazing periodic table. All right, you guys want this? It's nice. Do you notice something different about this periodic table?
Theme.
Yeah.
It's got different colors.
There's color.
Different colors. Okay. Less information. Some have more. Some have less. Right. This one has a good amount of information.
These are different colors.
All right. Do you notice that the numbers are flipped as far as where they're placed?
Yes.
So what I want you to, guys, listen. What I want you to make a mental note of right now is no matter if you're using a new periodic table, new to you, they are not always configured the same way. Commonly you will see the atomic number on the top and the atomic mass on the bottom. Is that the case with this one? No.
No.
On this periodic table, the atomic mass is at the top of the box, and the atomic number is at the bottom. So just remember, the smaller of the two numbers is the atomic number, because it's just protons. The bigger of the two numbers is the atomic mass. But your question, good question, you said it didn't make sense. The number there, let's look at carbon, since we dealt with it yesterday. Everybody see carbon? Number 6.
Yep.
The atomic mass is 12.011. Can you have 0.011 of a neutron?
No.
No. But it's awfully close to 12, right? So we would round to 12 because that's the most common naturally occurring isotope of carbon. It would be just 12. 6 protons, 6 neutrons. That's the atomic mass, period. Does that make sense?
Yeah.
The reason it has a 0.011, or some of these others have whatever decimal they have, is because there are other isotopes or other versions of carbon in this case. So 1 out of every 100 or so carbon atoms is carbon 13. What did I say? 1 out of approximately every 100 is carbon 13. So that isotope would have 6 protons and 7 neutrons. Follow?
Yeah.
But because it's only 1 in 100 carbons is that isotope, what decimal place is that first 1 after the 12?
100.
In the 100th place. Does that make sense?
No, it actually doesn't.
So the atomic mass in the periodic table is an average of the naturally occurring isotopes in the correct ratio that we find them. Okay, 99% of carbon is carbon-12. So the atomic mass, 99%, I'm still lost you, so okay, here we go. 99% of all carbon, we've got all carbon, 99% of it is carbon-12. Follow me so far?
Yeah.
Okay. Carbon-12, I need to get a better marker. Carbon-12's atomic mass would be 12, period. Dead on 12, because it's got 6 protons and 6 neutrons, right? About just under 1%. So I could put like 0.999 whatever percent of carbon is carbon-13. Carbon-13 is an isotope or version of carbon. It has an extra neutron. 6 protons, 7 neutrons. 6 plus 7 is 13. Its atomic mass is 13. Dead on. And then we have a third naturally occurring isotope of carbon. It's carbon-14, and it's like 0.000 whatever 1%. It's like 1 in a million, so I'd probably have to add another 0. Okay, is that carbon-14's atomic mass is what? 14. But when you average them together, you get carbon 12.001. Oops. 12.011. Does that make sense now?
Kind of.
It's an average. Which is why, especially in middle school teachers try to keep it simple. They say, hey, just take the atomic mass, round it to the nearest whole. So it'd be 12 minus the atomic number 6, and that's the number of neutrons it has, 6. But that's not always the case. But on average, that's more than average, right? Almost all the time, it's carbon-12. Chlorine wants to take or give? Take 1 electron, becoming a what? No, ion.
Ion.
I got that right.
Me too.
Guys, I gave you this definition just now. An ion is an atom with a different number of electrons than protons. So if chlorine picks up an extra electron, now it has now it has 1 more electron than it has protons, right? Which means it's going to have a -1 charge.
Yes.
Because electrons are negatively charged, right?
I agree.
Why do alkali metals and halogens react so strongly with other elements? All right, on your brand new shiny periodic tables. Okay, brand new and shiny. I want you to look at the very first group. So I want you to look like lithium down through francium. You guys see lithium through francium? Probably discovered by a Frenchman or something. I don't know, a French woman.
I'll see.
Now look also at fluorine through astatine. Is that right? Am I looking at that right? Yeah, astatine. You guys see that? Those are called the halogens.
Where's astatine at?
Yeah, where's the
AT.
Bottom right.
Atomic number 85, yes. You guys see it? So that vertical column from fluorine down are the halogens. Follow? You can write on this. If you want to write above fluorine the halogens, or the halogen group, or the halogen family, I don't care what you want to call it. And then over here, from lithium down to francium, those are the alkali metals. Everybody fine?
Yeah.
Why, the question is, why do the alkali metals and the halogens react so strongly with many other elements? Does anybody know? Yes. High reactivity. And why do they have such high reactivity? You're not wrong, but I'm pushing a little further here, okay? Yes, they have high reactivity, but why? Where are they? Look, the halogens are one column away from what?
The helium.
The metals.
Helium is an example of what?
Gases.
What kind of gas?
Oxygen.
Guys, this last column are the noble gases.
Oh.
What did we learn about the noble gases?
Helium.
Because of themselves.
They keep to themselves. They don't react well with other things. They don't react at all. Why? Because the electron configurations are perfect.
Oh.
The noble gases. You can write on this again. The noble gases, that far right column. The noble gases have a perfect electron configuration. What does that mean, perfect? It means they're stable. It means they don't want any more electrons and they don't want to give any up. They're perfectly stable. They don't react because they're so stable.
Perfect electron. What?
Think about that for a second. They don't react because they're perfectly stable. Do people who are really confident and like stable people, do they overreact with when people like are mean to them?
Yeah.
No, they're just kind of chill, right? Like, oh, hey, whatever, man. That's the noble gases. Right?
They're the cool kids.
The halogens are one away. Now, I know these are inanimate objects, but we can kind of think of them like people. They are so close. The halogens are so close to being perfect. They're so close to being stable that it makes them unstable. They are green with envy of the nobles. And they're so close. Does that make sense? If I put it that way? They have what's called an affinity for that electron configuration that the nobles have. They want to get there. Bad. But so do the alkali metals. And they just need to get rid of one to fall back to the ring under their valence shell so that they would also have a perfect configuration. Okay? So however you want to word that, why do they react so strongly with other elements? Because they are so close. They only need to either give up one for the alkali metals, or they only need to gain one for the halogens to be perfect. Okay, number 28, what does sodium and chloride make when they combine?
Sodium chloride.
Sodium chloride, and that is table salt.
Yeah. Yo.
Compare the properties of each of the following. All right, guys, states of matter. Think back to like elementary school. What are the states of matter?
Solid, liquid, gas, and plasma.
You got all four: solid, liquid, gas, and plasma. Now, also, he listed them in order from least energetic to most energetic. Think about it. If you have a solid and you add energy to it, think maybe like thermal energy, right? If you add energy to a solid, what will it do? It'll melt, or it'll skip the liquid phase and go straight to gas by burning or evaporating, right? It can skip it. And then if you heat a liquid, it will
Go to gas.
evaporate and become a gas. And if you heat a gas enough, it will become a
Plasma.
plasma. Now again, you can skip states of matter if there's enough energy involved. So we've reviewed states of matter. Sodium. Which one?
Solid.
Chlorine.
Yeah.
Gas. Together.
Solid.
A solid, yeah. Sodium chloride is a solid. It's the crystals that you like to put on your tongue with your food, right?
Yo.
Reactive or stable? Sodium.
Reactive.
Very reactive because it's an alkali metal. Chlorine.
Peroxide.
Reactive.
Very reactive because. Why do you keep saying
Wait.
peroxide?
Wait, what are we on? I was ready for practical use for sodium.
So chlorine, very reactive because it's a halogen. It's one away from being a noble gas, so it's very reactive. And then sodium chloride,
Reactive.
stable. What?
Oh, wouldn't it
What
be
are we
both
on?
of them or
Okay,
one?
no,
Where are
listen.
we at?
You completely missed the point of the video. You have two very reactive, very unstable elements in sodium and chlorine. But once they've reacted together, they become stable. Why? Because they now have the stable electron configuration of the noble gases. I need to do it now. I can't wait. So we're gonna do something to demonstrate this. Have like a empty page of notes ready to go.
Alright, I got you.
I'm gonna hit it now while it's fresh in your mind, okay?
Got it.
So a couple of you are still not quite getting, like, why could you have two things that are incredibly unstable all of a sudden become stable in table salt? Well, first of all, we can physically see that table salt's pretty stable because you put it on your tongue and it doesn't explode, right?
Yep.
If you had pure sodium and you threw it in your mouth, you're gonna have a bad day, right?
What would happen?
It would react violently with the water in your mouth.
Oh. You would die.
Pop, 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 as in you're gonna go to the hospital.
Oh.
Wait, so like, does it explode in your mouth?
Peroxide.
Yeah, it would react violently, explosively with the water in the
We should do an example.
saliva.
We should do an example.
It's like eating juniper.
All right, guys, you ready?
Yep.
Okay, we're gonna draw a Bohr model
Okay.
named after Niels Bohr, the genius that came up with this way of modeling atoms. All right. So to draw a Bohr model, the first thing you do is put the atomic symbol. So the atomic symbol of sodium is what?
NA.
Na. When you are, guys, when you are writing atomic symbols, if it's a two-letter symbol, the first letter is always capitalized, the second letter is always lowercase. So we have sodium. Chlorine is what?
Neon.
CL.
Cl. In a Bohr model, all we're concerned with is the electron configuration, right? So we're not going to draw a bunch of dots for protons and neutrons. We're just going to say, hey, it's sodium. We can look that information up if we need to, right?
Yeah.
Sodium and chlorine are both in which row of the periodic table?
Which like
The third. Which horizontal row? The
Oh,
third.
third.
Which means they're going to have 3 energy levels for their orbitals or their rings. 1, 2, 3.
2, 2, 8.
That's a pretty good circle.
Okay, thank you very much. I practice all the time. The first ring is representable or represented, I guess how you look at it, by the first row. How many elements are in the first row of the periodic table?
2.
2. So we said you can put 2 electrons there. So we have 1, 2. The second row has how many
8.
elements? 8. So the second ring can hold 8. We're going to double them up. We're going to go by pairs. Why? Because that's what Niels Bohr did, okay? He gets to determine how the model is made because he came up with it, right?
Yeah.
So we'll respect the model. Correct me if I'm wrong, peer tutor. Are these supposed to be together? I forget.
No.
Okay, all right, well,
I don't think my chemistry teacher.
okay. So we keep the first one separated anyway. And the same over here for sodium. We have 2 on each side here. In reality, of course, the electrons are flinging all over the place, like chaotically. But in our model, we want them a little bit more orderly, so we can count them and check them out, okay? Sodium, we've got 2, and then 8. How many should be on the outermost
8.
shell?
8. 2.
How many electrons does sodium have?
8.
8.
look at your periodic table.
Where's sodium?
Find sodium.
11.
First.
You already told me, yeah, it's 11.
11.
So I've got 2, 8 makes,
10.
2 and 8 makes
10.
10. So I need
One more.
one more.
Whoa.
That is a Bohr model of sodium. This represents the electron configuration of sodium. Okay? Chlorine, 17. And right now we have 2 and 8 makes. So we need 7 on the outermost. So we're going to put 2 here, 2 here, 2 here, and 1 here. But, so before I say but, this is the electron configuration in a Bohr model for chlorine. Everybody clear?
Yes.
These are Bohr models of sodium and chlorine. Sodium, if it lost this electron, it would have, this would be its new valence shell, the outermost shell. The word valence, if you need to put this in your notes, or if you remember, valence means outermost, yes. So if sodium lost this one, it would just have these two, right? These two rows, or these two rings. And it would have the exact same electron configuration as neon, a noble gas. So it would be completely stable if it got rid of this. So sodium is looking, like if it were a person, it'd be actively looking to dump this stupid electron. I can't wait, oh my gosh, I want to get rid of it. Chlorine, on the other hand, has a blank spot just waiting for one more. Because if it has one more, it'll have the same electron configuration as argon, which is also a
Noble gas.
noble gas with a perfect stable electron configuration. So it is ready to receive. Yes, please. So if these were people, they'd be like, let's make a deal. Like the game show, right? Let's make a deal. Gimme, gimme. Yes, please. Take it. Okay? Now, let's make this deal happen. We're going to put our electron there. That one is gone. We're going to leave the arrow showing where it came from, okay? What just happened to these atoms?
They changed.
Into what?
Ions.
They changed into ions. Very good. These two atoms just became charged particles. They became ions. How many protons does chlorine have?
17.
17 protons. And protons have what kind of a charge?
Negative. Positive.
Positive.
Positive. Positive protons, right?
Yeah.
How many electrons does it have now?
16.
Wait.
It just got one from sodium.
17.
Oh, yeah, it's just the same.
Wait.
8.
Electrons and
Count.
protons have the same.
1,
1, 2, 3,
4,
4, 5,
wait.
6, 7, 8.
1,
9,
2,
10, 11, 12,
3,
13,
4, 5,
14,
6, 7,
18.
8.
Now, I heard somebody say, but they have the same protons and electrons. No, that's when they were an atom.
Wait.
That's when I drew it as a Bohr model, just as chlorine by itself. But it just took one
18.
from
Or
sodium.
where?
So it has 18, and electrons have what kind of charge?
Negative.
Negative.
So
One.
what total charge does this chlorine ion now have?
Negative 1.
One
Negative 1.
Negative 1 ion. It's a negative 1 charged ion. How about sodium? How many protons does sodium have?
How many protons?
Protons.
1, 2, 3, 4.
Sodium.
10.
Sodium.
Oh,
Protons.
wrong one.
Oh, 11.
11.
Ah,
And protons have what charge?
Positive.
positive.
How many electrons does it have now?
10.
10.
10. And what charge do electrons have?
Positive.
Negative.
Or
What are you
negative,
wrong
negative,
about?
So what is its overall charge?
1 ion.
Positive 1. It is a positive 1. I can't spell.
So they cancel
Huh.
out.
They, guys, together they cancel out. Together they cancel out. But individually, they are charged, and they have opposite charges. In electromagnetism, what do opposites do?
Connect.
They attract. Okay? So this, because they are ions and they have attracted and bonded to each other, we call it an ionic bond. This bond between them, caused by their differences in charge, has bonded them together. Make sense?
Yeah.
What, are we running out of time or something?
Yeah.
We still got a couple minutes.
3.
Moving on.
We're still in practical use.
Where are we? Are we in practical use? Sodium.
Peroxide.
Peroxide.
But well, if it's with peroxide, isn't it no longer just sodium by itself?
Sodium.
Is it not peroxide?
It's some clean.
Peroxide is a molecule of oxygen. Did you know that?
I know what it is.
What is
Hey,
it?
cleans out my foot. Yeah,
Chlorine.
clean
Can you use chlorine for anything by itself?
Yes.
For what?
The pool.
Pool chemicals, right? You put the chlorine in there, it starts to kill stuff because it's stripping electrons off of it.
Tastes good.
I wouldn't recommend it. Sodium chloride.
Dehydrated.
Table salt.
It was
Sodium. Hey guys, sodium and potassium. Have you ever heard the word electrolyte before?
Yeah.
Yes. I have to have it.
So potassium and sodium are both examples of electrolytes. I'll throw another word at you. Electrochemical.
It's a chemical compound.
So in your body, signals are sent from your brain to your muscles to do certain things, right?
Yeah.
It's sent electrically through chemicals that can carry that charge. They can send the signal, all right? Electrochemical signals. If you don't have the right amount or the right proportion of potassium and sodium in your body, the signal can be interrupted. So has anybody ever had cramps before?
Yes.
Charlie horse, right?
Yeah.
So what's happened is the signal has been sent to flex or contract a muscle, but then the signal to release got lost in the electrochemical pathway. It got disrupted. Does that make sense?
Yeah.
So it seizes. Okay. Next page. We should be able to finish this. What is ANFO? An explosive. Moving on. Number 31. It's a nitrogen-based fertilizer that can also be used as an explosive. 31. What do each of the spikes on the ion chromatograph from the video represent? Each spike is a different element. Okay, so you remember the magic swab she talked about? They wiped it down, the remnants of the car. They put it in a solution and then squirted it into the machine. And it detects what's present. And based on what elements are present, they can determine what explosive compound was used. 32. The minus sign. Tap it. The minus sign is not a minus sign. I need you to change it. Okay? It looks like a minus sign. I need you to either add a line like that, or you can make it a full-on arrow. It doesn't matter to me. When you take chemistry, your teacher might be more particular about it. That means yields. Okay? So that symbol in the middle is not a minus sign. It should be a little arrow. It means yields. So you have a couple of molecules reacting together, and that reaction yields products and a big, huge release of energy, right? The products it releases are not harmful at all. Water, nitrogen, and oxygen. We breathe all three of those every breath we take, because there's water vapor in the air, there's oxygen in the air, and there's lots of nitrogen in the air.
What's nitrogen?
To us, it's just an inert gas. It doesn't do anything. It just basically fills the air with, otherwise there wouldn't be, it adds mass to the air and pressure.